I'm ready to start in a second. Are there questions about anything before I get going?
Sunday's lecture will be when?
3 o'clock. Enough time for people to get back from wherever you are and still get here. No. Are you nuts? Well, you can hang around and ask questions, but Tara actually is probably going to show up, so we can do informal things, but there's no formal recitation. Okay. Generating functions is another example of something that the book puts in a place where I think it shouldn't be exactly. It is a technique that connects to solving recurrence equations. It is one more way to solve recurrence equations. It's a really, really powerful technique, but it's hard to appreciate generating functions until you already understand everything you need to know about counting. What generating functions really are is a way to leverage what you know about algebra to apply to counting. It's a way to make a connection between counting problems and algebraic formulas, so that when you manipulate the algebraic formulas by the stuff you learned in high school, you try to understand how that relates to the counting problem that the algebraic formula was connected to. So it gives you the ability to take a tool that you're very familiar with, the algebra tools, and yank them on counting problems and really get some interesting things. So for the first, I don't know, hour or so, you're going to see it applied to situations that you could have solved without generating functions. But at the very end of this lecture and a half, as long as it takes me, we're going to solve that recurrence equation about the parentheses and about the binary trees that goes on and a long sum that we couldn't solve with any other method. And the generating functions will really show their power, and you'll see where the algebra connection really comes in. So where you'll see it's really, really used is in that problem, which we couldn't solve in any other way up till now. All the other problems are kind of like an intro until then. All right, so first I got to give you an idea of what this is all about and what's happening here. So are there questions so far? Everything we've been doing with recurrence equations, you know, a recurrence equation, you solve it for t of n, and then you can plug in various n's. You get t of 1 is this, t of 2 is that, t of 3 is this. If it's like Fibonacci numbers, for example, you know, the values go 1, 1, 2, 3, 5, 8. If it's triangle numbers, they go 1, 3, 6, 10, 15. So you can think of counting problems or solving recurrence equations in some ways as generating sequences. Generating function is a way to represent a sequence in a way that seems completely twisted, in a way that seems more complicated than you would need, but a way that actually pays back later with all the complication that you use with a lot of power. So here's what I mean. Let's say you have the sequence of triangle numbers, 1, 3, 6, 10, 15, 21, etc. So a way to represent this as a generating function, here's what a generating function means. It's a polynomial whose coefficients on here's what it is. Whose coefficients on the polynomial terms are the same as the numbers in the sequence. This is the generating function for the triangle numbers. So in this case, if we call these triangle numbers t, this would be t0, this would be t1, this would be t2. This series here?
I'm assuming that you're going to solve for x at some point.
No, we're not. No. In fact, you never do that.
Right, because the series, you don't know the length of the series.
You're right. You don't solve it for 0. You just use them and you manipulate them and you get new functions that have new numbers on the coefficients. That's how we're going to use it. You'll see how we'll use it in a couple minutes. Well, yeah, be patient. So here's the thing. In front of the x to the 0, you get the t0 number. In front of the x to the 1, you get the t1 number. In front of the x squared, you get the t2 number. Okay? It's just a way of writing a sequence in terms of a polynomial. Now, why would you want to do that? You'll see in a little while. Questions so far? Okie doke. Let me ask you one. Here's Pascal's triangle. Here's a finite sequence, 1, 2, 1. What's the generating function for that finite sequence? 1 plus 2x plus x squared. And that happens to also be the same as this. Right? What's the generating function for the third row of Pascal's triangle? Remember we talked about this last time, how multiplying this out gives you the same as these binomial coefficients? That was the binomial theorem. So one thing that you already know about generating functions is that if you want the kth row of Pascal's triangle, and it's a finite sequence of numbers, and you want the generating function for that kth row, it's exactly the function 1 plus x to the k. Okay, so you can have infinite generating functions, you can have finite generating functions. And the actual coefficients here, as you probably know, are k choose 0, k choose 1, k choose 2, all the way up to k choose k. Right? That's the kth row in Pascal's triangle. That's some review, but make sure everybody remembers. This generating function generates these coefficients on each of the terms as you go from the constant term up to the x to the kth term. Okay, questions so far? Good. Keep wondering where it's going, because it'll get somewhere soon. Okay, here's a counting problem. You want to get 6 different numbers. You want them to add up to 20. And each of the numbers has to be in between 0 and 8. Remember these kind of problems? We did a lot of these kind of problems. Remember how to solve these? The greater than constraints were easy to handle. Right? The greater than constraints just made us take a little bit away from this number, and we were able to solve it. It was the less than constraints that were a pain in the butt. Right? The less than constraints, we solved it in 2 different ways. One way was reversing it and doing inclusion-exclusion, turning it from ands to ors and doing inclusion-exclusion. And the other way was just doing lots of cases. If ni has to be less than or equal to 8, okay, so n1 can be 0, do all the cases. n1 can be 1, do all the cases. n1 can be 2. And that's a sometimes very slow way, but it would also work. That's a direct way. We did it both ways when we solved this problem. We did it the direct way, where we did it in cases, and we did it inclusion-exclusion. Now we're going to do it using generating functions. Now, I got to tell you that the method that I'm going to do here is not going to be easier than either of our methods. It's simply going to show you a connection between counting and generating functions. It's not going to be so useful as far as the calculation or the computation goes. It'll be just as hard to get the answer with a generating function as it was with inclusion-exclusion or with the cases. But it will make a connection between these 2 seemingly separate things. So, here is the connection, and I'll explain exactly how it works in a second, but first let me give it to you. Here's a function, 1 plus x squared plus x cubed all the way up to x to the 8th. Come on, almost. There it is. All right. And I'm going to multiply this by itself 6 times. This function, if you multiply it all out, polynomial, and when you're all done, look at what's in front of the x to the 20th term. That's the answer to this problem. And I'm going to explain why in a second. But first, get the connection. Here's a problem that's completely a combinatorial problem. It's a counting problem. I turned it into an algebra problem. Here's a polynomial to the 6th power. Multiply it out. When you're all done, look at what's in front of the x to the 20th. That's the answer to this problem. Now let's see why. What happens in the algebra mimics what's happening in this counting. And that's why we're leveraging the power of this algebra. Because there might be an easy way of doing this multiplication and getting this number. In fact, there is no easy way, but in other situations there is an easy way of leveraging the algebra. In this case, it's just as big of a pain to multiply this out and find this number as it is to solve this directly. But that's not the point. The point is I want to make the connection between the 2 seemingly different subjects.
So the coefficient corresponds to which part exactly? The coefficient on the x to the 20?
It corresponds to how many solutions there are to this equation.
Okay.
How many different ways we can solve that equation. All right. I want to give you a sense of this intuitively, and then I'm going to do an example in much more detail so you'll see exactly why these two things are really the same. So first, intuitively, what's going on? How do you get an x to the 20th term from multiplying something from here times something from the next one times something from the next one? You've got 6 things you multiply together, 6 possible x's. Give me one way to get x to the 20th. You could take, say, x to the 8, x to the 7, x to the 5, and then 1 times 1 times 1. All right, good. Baruch gave me 6 different things. I took x to the 8th from the first one of these. I multiplied it by x to the 7th from the second one. Multiplied it by x to the 5th from the third one. Multiplied it by 1, 1, 1 from the 4th, 5th, and 6th. When I multiply these all together, I get 1x to the 20th. Okay? What does this correspond to? This corresponds to, as far as counting, that n3 is 5, n2 is 7, n1 is 8, n4, 5, 6 are 0. Every possible combination of multiplied monomials, God knows I never thought I'd use that word, just means one of these x's. Every possible combinations of those corresponds to a choice of a value for one of these n's, where the choice of the value is the exponent that you chose. 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. 0 through 8 for each one. The choice of each of these 6 can be 0 through 8, corresponding to the exponent on the x that you chose. When you choose 6 of these, if the exponents add up to 20, that means these numbers added up to 20. If the exponents add up to 20, then when you multiply that together, you get one more x to the 20th term. How many different ways are there to choose these exponents so that you get x to the 20th? That's exactly how many values are going to be here. That's exactly the number that's going to be here. How many different n1s, n2s, n3s, n4s, n5s, and 6s make this equal to 20? That's going to be the same number that appears in front of that x to the 20th. I'm going to do this again in a smaller example, but I wanted to give you a general intuition first. So let me stop for a second. This is a deep idea, and you can get it right away, or it can take some time to sink in. So let me stop for a second. Other questions so far? Yeah, Donna.
Does that include all the permutations?
Meaning what? It includes every possible way for me to choose n1 being 0 through 8.
So it will also include 1 times 1 times 1. Like a different order of the same.
Sure.
That'll be counted as another.
That'll be counted as another one. And it should be. Because that means I chose 0 for n1 and 8, 7, 5 for 4, 5, 6. Yes, it will count it, and it should count it.
So order counts in this answer.
Yes, because all these ni's are distinct. Right. Yes, order counts in this answer. These are distinct. Yes. Other questions about this? John?
I missed how you pulled out that expression.
Where I got this from?
And particularly the 3 ones on the end.
I asked how we figure out where we get an x to the 20th term from. So there are 6 multiplications that occur. One from here, and then etc. 6 different things from each one of these terms get multiplied together. Well, there's a lot more, but if you want to just pick out one x to the 20th term, you can pick out, say, an x to the 8th from here, an x to the 7th from the next one, an x to the 5th from the next one, and a 1 and a 1 and a 1 from the 4th and the 5th and the 6th.
I'm sorry, yes, you got that whole thing chunked out 6 times.
Right, right. So each one of these represents a choice of one of the 9 values in one of these terms, and we have 6 of those choices. So I picked one of the 9 values for each of the 6 choices, and I wrote them here. Every unique choice of those values 6 times corresponds 1-to-1 correspondence to a set of values for these n1 through n6. And vice versa. If you give me a set of numbers here, I can come up with a polynomial choice from each one of these 6 terms. And what's more, since these numbers have to equal 20, those x values, exponents, will add up to 20. And that's exactly what I mean by counting up all the x to the 20ths. Does it make sense? Are there other questions? It's a hard idea. Other questions? Yeah, Tony.
Can you do it with different constraints for each n?
What do you think?
Yes.
Yes. So let's do that right now. Okay? And in this one, I'll really do the example in more detail if you're still not with this idea yet. So same kind of problem. We're going to distribute 8 cookies to 3 kids. Each kid gets 2 to 4 cookies. How was camp today? It was great. We got 2 cookies. All right. This is the same kind of question. It's like this. x1 plus x2 plus x3 equals 8. And the constraint is that every kid is bigger than or equal to 2, less than or equal to 4. I just wrote it like this for the heck of it to remind you that these things correspond to distributing indistinct things to distinct things. Okay? So this is what you meant, right, Tony? This is.
Yeah, except I wouldn't have used x because you use x down here.
Oh yeah, I wouldn't have used it either. You're right. Bad letter. What do you want to use? T for Tony? They're great. All right, there we go. We can also change these constraints for every t, and we'll see how to do that in a second too. But what would this be like? Try to make the analogy. Even if you don't understand the idea, you can probably get the analogy down if you really think about it. What would the polynomial be like here that's going to generate this in front of the, first of all, what's it going to be in front of? Which term? Not x to the 20 this time, but x to the 8th, right. And what's the polynomial going to be? X squared, x cubed, x fourth, because your choices here are not 0 through 8 like they were before. Your choices here are 2 through 4. How many times do you have a choice? 3 different kids. You have to make a choice for each kid. Okay? So this is the generating function for this problem. Yeah, what's your question?
I think what I said was using a different constraint for each member of...
We're going to do that.
Oh, okay.
We'll do that in a second.
Okay.
You get this so far? Let me go through this in a little more detail to make sure everybody gets this idea. And then we'll do an example where the constraints just differ one by one. And the number in front of the x to the 8th would be 6. So it's a whole bunch of things plus 6x to the 8th. And 6 is the number of ways you can distribute these things in 2 to 4 cookies a kid. All right, now let's see what that means. The way to understand this, if this wasn't clear before, if this argument wasn't clear, is to, in your head, call these things A, B, and C, just so you don't lose track of where they are. And let's go ahead and write down every possible combination in this cube that's going to give us an x to the 8th term. Let's write them all down. There aren't so many. There's only 6, so we could write them down. I don't know how many there'd be in that example. It'd be too many. So what's 1? We get xa squared, xb squared we could use, and then we need xc to the 4th. Let's just be very methodical about it. xa squared, xb cubed, xc cubed. Next one, xa squared, xb to the 4th, xc squared. How much more do I have? I only have 3 more. It shouldn't be so bad. xa cubed, xb cubed, xc squared, xa cubed, xb. Can I do x? can I just do xb to the, well, I guess I missed one. xb squared, xc cubed. Which one did I miss? X, xa 4, xb squared, and xc squared. These are all the possible combinations as I go multiplying one from here, multiplying one from the second, multiplying one from the third. If I combine them all, these are the ones that add up to 8 with the exponents. A from the first, B from the second, C from the third. A from the first, B from the second, C from the third. A, B, and C represent the particular x I'm talking about, and these exponents represent which one of them I chose. So is that, that's not going to help. I really mean this, right? This is what I meant to write, sorry. I cubed it out. You always choose an XA your first time. You choose an XB your second time. You choose an XC your third time. So this represents that you choose the square from the first one, you choose the square from the second one, and you choose the fourth from the last one. You can thread your way through. There's only so many possibilities that add up to 8. And these are all of them. But labeling the x's in each subsequent term gives you a chance to see exactly what's happening. All right, so I didn't mean ABC there. That's a mistake. So fix that. Sorry. Teresa.
It almost seems like you're just adding notation to what you were doing last week with the box technique.
That's true. That's true. And the moral is that sometimes notation becomes really powerful if it connects to a whole bunch of other tools that you already know work for that notation. So we're just throwing everything we did before in a new language, the language of algebra. But you know all sorts of things you can do with algebra. And soon enough, there's going to be something we can do with algebra that will take us into the realm of solving a problem that we couldn't solve before. So by changing our language, this language is better for some things that our old language was, and it's going to take us to new places. So you're right. In some ways, we're just restating what we all knew before in a different language. All right, questions about this? Gador, you have a question? Thinking? Let me go back here. I'll ask you guys another question. Back to this problem. Okay, let's say x1 has to be between 3 and 7. x2 has to be between 0 and 8. Oh, yeah, ends. Sorry. I'm using D for Donna now. Okay, let's say I make a combination of constraints. You all probably know that you can solve these kind of problems using a combination of permutations, combinations, and inclusion-exclusion. It's a horrible kind of a problem to have to do. It's lots and lots of cases. You have to think about it. But now we can just put it all in terms of polynomials. What polynomial is going to generate the answer to this question? It's still going to be what shows up in front of the x to the 20th, but what polynomial do we actually multiply out to see what's in front of the x to the 20th? What do we use for n1? The choices are 3, 4, 5, 6, 7. So as far as the polynomial exponents go, the choice is x cubed, x fourth, x fifth, x sixth, and x seventh. Times. What do you get for this one? 1 all the way through x to the 8th. What do you get for the next one? X to the 6th plus x to the 7th. And the last one, x squared plus x cubed plus x to the 4th, because you have 2, 3, or 4 that can be the values there. And you have 3 of those. So I cube that. Times, times, times. This long polynomial is the generating function that would give us the answer to this question if we looked at the value in front of the x to the 20th term. Right? Is this a better idea? Teresa was saying, well, now you just turned it into some algebra thing, but it's really the same idea. And if you actually tried to solve this, you'd end up doing very similar to what we've been doing before. You'd multiply it out, and you'd see all these cases. It isn't much easier to multiply this out than it is to do all the cases of the counting in the first place. Granted, that all may be true. And the power isn't shown in these examples. It's just a way of letting you see the connection between algebra and counting. Yeah, Seth?
Are those x's to the right of parentheses x's, or we're supposed to assume those parentheses are multiplied by the other things in parentheses?
These are multiplies.
Okay, those are all.
Yeah, those are multiplies, not x's. Right. This times this times this times this.
This one at least would be easier to write a program for, probably.
Probably, right. Right. And you're going to see, you remember the stuff you did with streams and scheme? The stuff you did with streams is going to start landing into this topic in about 10 minutes. And it's going to come in a really striking way. Questions about this so far? Todd, you look pensive. You have a...
If Joey has to get twice as many as Tony,
Oh.
is this method applicable?
I don't know, is the short answer. Let me think about it. I'm not sure. Good question.
Can't you just use another variable instead of a number? I mean, mixed, that is mixed.
Like if n1 has to be bigger than or equal to n2?
Right, well.
Or twice n2? Or
The constraints, yes.
I guess I can try to convert it into a set of constraints like this, but I'm not sure. I don't see any way to do it automatically.
N1 between greater than or equal to a over 2, less than or equal to a, and then N2, interesting. Yeah.
I'm not sure, because you get ands and ors. These are always ands, and it gets a little complicated. I'm sure there's a nice way to think about that, but it's... Yes, Neil. Sure. Oh, yeah. Oh, sure. Yeah, this stuff, this kind of symbolic calculations were originally in a program, I guess, called Maxima many years ago, maybe in the mid-'70s or early '70s. This started to get done, and since then, like things like Mathematica have just become, huge commercial projects where they do much more than this. I mean, they'll actually manipulate this out and give you numbers in front of these, try to give you closed form formulas in front of, do all sorts of clever things. There's even new mechanical techniques for taking any kind of a sequence and mechanically computing the recurrence equation from the sequence, which was always thought to be something in the realm only of mathematicians, that it required cleverness, that there wasn't a mechanical way to do that. But there is, it turns out. And that's not at all easy. That's in the last 5 years. So there's a lot of neat things you can do with computers. Yeah? Oh, okay. So that's 20 years ago, probably. No, it might be more. Maybe 25. Yeah. All right, questions. More questions.
Why are there weird mathematicians hanging out on
Yeah, what are you guys doing here? Go ride the red line. I was going to go to ADU, but I heard the red line's even better. Except they don't have $800 chairs on the red line. That's it. All right. All right. I'm going to come up with some functions representing sequences. The way you get a sequence from a function is you just plug in the numbers 0, 1, 2, 3 into the function and see what comes out. So I'm going to write some functions up on the board, and you tell me what the generating functions are. These are going to be going from easy to hard. So here's one function. A of n equals 1. Anything you plug in, you get 1. What's the generating function look like? If I plug in 2, I get 1. If I plug in 3, I get 1. It's not just 1. It goes on and on and on. Okay, here's the generating function for this particular function. That means if I plug in n, I go look at the term that has n in the exponent, and I look at the coefficient in front of it, and the coefficient's always 1. This is the sequence 1, 1, 1, 1, 1, 1, 1, 1, 1. Everybody get what I mean? Okay. Yeah. No? All right, let me say it again. This is a function. You can make a chart. Here's n. Here's the value of the function. 1, 1, 1, 1, 1. That's the sequence I'm talking about that represents a function.
And so n is the exponent, so x to the n.
Right. If you want to know what a of n is, you look at x to the n and you look at what's in front of it. So the generating function for this has a n in front of the term x to the n. If you wanted to write it, it would look like this. That's the generating function. I didn't want to write this symbol down before because it's probably more confusing than it's worth, but it just means this. It means that the coefficients of these values, as n ranges from 0 to infinity, show up in front of the appropriate term of the polynomial. So if the coefficients are all 1s, then 1s show up in front of all the polynomial values.
If there's no constraints, then it's an infinite series.
Well, here we're not even connecting it to counting. Here we just went back to generating functions. So, right, and if there's no constraints, an accounting problem, presumably.
On the domain of n.
Right, if there's no constraints on this counting thing, it might go forever, right? What's that, Chris?
On the function, I'm not thinking counting.
Oh, no, there's no constraints in the function. It just goes on forever, right? In this case, right? Okay. Here's something that you should know from algebra that makes these kind of infinite things suddenly turn finite. How do you prove this? You proved it back in, I don't know, the first week of class or something. There's a lot of ways to prove it. You could prove it by induction. You could prove it by multiplying it out. What happens when you multiply this times this? You get a copy of this minus a copy of this shifted over one to the right. All the x's fall out and you get 1. Multiply this out and you'll see that it works. So that's something you should know. This very basic generating function is equal to something that's more finite looking. And we're actually going to use this in the opposite way. We're going to come up with generating functions that solve problems and then convert these generating functions. When we see 1 minus x, we'll know that that means 1, 1, 1, 1, 1. Here's some other ones that you should be aware of. You might be able to figure this out on the spot. You might not. What do you think this one turns into? Here's what it turns into. Do the same trick. Multiply this out, and everything shifts over 1 and cancels out. So if you have a 2 down here instead of a 1, then instead of 1 showing up here, you get 2, and then 2 squared, and then 2 cubed. Yeah?
I'm a little confused. Let's say you plug in x equals 10 for the top one, and you get 1 over, it's negative a 9. And then it seems like that's a fraction. And then you're making numbers bigger than 1 on the right-hand side. So.
Yeah, you can't just plug in numbers, because this doesn't really work for numbers in certain ranges.
Okay.
It only works for between 0 and 1.
Right, it only works for numbers between 0 and 1.
Okay.
It only converges for numbers between 0 and 1. It diverges for other numbers.
Does it work if it's negative? Wasn't negative a half work?
Like if it's negative 2?
No, negative a half.
Oh, negative half, it works okay, sure. I think it works for negative a half. It works between negative 1 and plus 1. It works in that radius of 1. Okay. What do you think it is if it's 1 minus, say, ax? 1 plus ax plus a squared x squared plus a cubed x cubed. This shouldn't be some kind of weird mystery. How do you know? The way to figure out what's going to work here is completely algebra. It's got nothing to do with counting. It's got nothing to do with a new idea of generating functions. Multiply this through, you get 1 copy of this. Multiplying it through again by ax is going to just shift everything over 1. And you subtract because it's a negative. So all the x terms cancel out and you get 1. So here's a few you should remember. This is the most general case of it, that if you see a generating function 1 over 1 minus ax, you know that the coefficients that they generate are a squared, a cubed. That's very, very, very useful because we're going to solve problems later and we're going to be gearing and aiming toward getting things like this because we know what they actually generate. Here's a situation where we don't have to figure out how to multiply the thing out. We know exactly what would happen if we multiplied it all out. It would look like this. So here's what we're going to be heading towards later on. Things like that. Yeah, Baruch.
This is geometric sequence with ax as the geometric factor.
Exactly. This is a geometric series with ax as the multiplicative factor.
And it's sum of geometric sequences.
Absolutely. Right. Right. So it's really just an example of geometric series.
So the corresponding functions are a to the n.
The corresponding right. So the corresponding function here is, instead of 1, this would be, a of n would be 2 to the n, and here a of n would be a to the n. Good. And this is really 1 to the n. It's the same as 1. So if you have these functions, here are the coefficients that they generate. Those are going to be our ABCs for generating functions. All right, questions? Okay. Here's a generating function. I'm not writing it out as a polynomial on purpose, because I want you to try to figure out what the coefficients that this generating function generates. What are the coefficients in front of the 1 and the x and the x squared and the x cubed? And how would you figure something like that out? Look over here. This generating function is this one times itself. Right? It's 1 plus x squared, dot, 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 times 1 plus x squared, dot, 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 dot. Multiply those two together, term by term. What's the constant term going to be? 1. What's the x term going to be?
2.
How'd you get that? How do you get all the x terms? How do you know it's 2 of them? X times 1. X times 1. There's no other way you can get x from multiplying those two things out. How many x squared terms do you get? X squared times 1. 1 times x squared. X times x. 3. How many x cubed terms do you get? 6? How do you get 6? Count them for me.
Triangle number?
No?
Well,
Good guess. The next one will be a triangle number. How many x cubes do you get? Right, Alex. 4. Right. 1 times x cubed. X times x squared. X cubed times 1 and x squared times x. In general, what do you get for the next term? Be 5x to the 4th, 6x to the 5th. What's the function that corresponds to this? We'll call it a of n again. What is it? N. If I want, well, what is it? If I go here to the first term, the exponent 1, it's 1 more than that. If I go here where the exponent's 2, it's 1 more than that. So the function's m plus 1. This function was a of n equals 1. This function is a of n equal m plus 1. I want you to think about how we got from here to here again, and I'm going to write it down in more detail. I'm going to write down the coefficients here in this way. I'm going to call this, I'll call this a of n equals 1. And I'm going to give this a new name. We'll call it b. A0 is 1. A1 is 1. A2 is 1. A3 is 1, etc. Now, how do we get b of 0? Don't tell me that it's 1. I know it's 1. But how do we get it? we took a of 0 times a of 0, right? How do we get b of 1? We took a0 times a1 plus a1 times a0. Now, what? We took this one here. It's too hard, too tricky? Okay.
Just ringing bells that I prefer not to
Oh, yeah. Ding those bells. What's the next one? You start with this coefficient. You multiply it by the square coefficient. A0, A2, A1, A1, A2, A0. B of n. Now we're going to use this notation. I'm going to write it here. B of n. This is important. We start out with A0, right? And we connect it with something else. So let's call this I equals 0. We start out with A0, and it gets connected with what? If I is 0, we have n here. If I is 1, we have n minus 1. If I is 2, we have n minus 2. The sum of these two things have to add up to n. And we're going to do this from I starting at 0 all the way until I gets to n. That represents B of n. Let me stop for a second. This is an important idea, and it's complicated in its algebra, so take a look at it and think about it again.
So what we did is we went from like the equation with the 1 over 1 minus x squared, and we expanded it out by multiplying the two things that we knew it was the square of. And then we turned that into the b of n.
Then I calculated the coefficients in that new expansion. And now I'm telling you exactly how I calculated each coefficient. That if I wanted the fifth coefficient, I got it by taking the first one from here and the fifth one from there, or the 0th one from here and the fifth one from there, plus the second one from here and the fourth one from there, plus the third from here and the second from there, plus the fourth from here and the first from there, plus the fifth from here and the 0th from there. Add them all together, and that gives me the fifth on my new function. Now in this case, all the a's are 1s. So when you do this, every one of these products is 1 times 1. So that's why b of 2 ends up being equal to, not 2. B of 2 ends up being 3 because you start from 0, you go to 2, 0, 1, 2. That's 3 times. You add 1s up together. Every single time you do this, starting with all 1s, you end up getting n plus 1. So in our case, b of n is equal to the sum I equals 0 to n of 1, and that equals n plus 1. And that's how we got this n plus 1. The reason I did it first in the brute force way and now in this general way is because I want you to see what happens when you multiply two generating functions together. When you multiply two generating functions together, the new constants you get can be computed according to this formula. And this kind of weird convolution should remind you of all those hard problems that we haven't solved yet. Right? Of the binary tree recurrence, of the parentheses recurrence, and of the matrices recurrence. They're almost the exact same thing. You start with a0, you get an minus 1. You go to a1, you get an minus 2. So it's very similar to what we did there, and that'll come back, and we'll do that later. But let me stop for a second. Again, this is what happens when you multiply two together. I think I need to do another example of this, judging from all the faces. So now we're going to do this. Let's say I square it again. So now I have 1 minus x to the fourth. I'm going to take this sum and square it. Without writing out the x's, ask yourself, what is the number in front of, say, x to the 5th? Everyone understand what I'm saying? We're going to do this by working through our idea before about how to multiply two generating functions together. I have two generating functions. 1 minus x squared, 1 over 1 minus x squared, and another 1 minus 1 over 1 minus x squared. I'm going to multiply these two together and try to figure out what's in front of x to the 5th. How do I do it? We'll call this c, these. What's c of 5? What's the thing in front of x to the 5th? It's going to be b of 0 times b of 5. What does that mean? I guess I couldn't go back to here to show you. What does that mean? It means this 1 times the number in front of the 5, which is a 6. That gives us 6x to the... I'm going to write it out again. You're multiplying this times this. The first thing you do is take the 1 and multiply it by 6x to the 5th. That gives you 6. That's 1 times 6. Plus, the next thing you can do to get x to the 5th is multiply what's in front of the x by what's in front of the x to the 4th. So that's going to be 2 times 5, or what we call it, b of 1 times b of 4. b of 2 times b of 3, b of 3 times b of 2, b of 4 times b of 1, and b of 5 times b of 0. There should be 6 terms altogether. I went from 0 to 5. Let's add these all up. 1 times 6. 2 times 5, 3 times 4, 6 times 1, 5 times 2, 4 times 3, 7, 17, 29, 39, 41, 51, 57. Somebody check. It's double. It's tough to get 57, huh? Duh.
I think you started with 7. You should start with 6. It's just
56. Let's look at this in a different way. These numbers are the sum of n plus 1, right? As n goes from what to what? As n goes from, n plus 1, back up. I equals 0 to n. What is b of I? B of I is I plus 1. What's b of n minus I? N minus I minus 1. What we're really doing here is doing this sum. Now you could go ahead and multiply this out and do this sum using all these other techniques we did at the beginning of the course too. But here we just did it with numbers and we got 56. All right. So that's one of the hardest things about generating functions, is to see that when you multiply them together, the new coefficients are calculated in this way. Let me do some easier things. I jumped to the hard thing, and now I'll do some easier things to ease your minds. I can see that this is tough. This will relate back to streams that you did last year. I love that. Last year, yeah, we had a whole year to let it sink in. You know that 1 minus x is this formula, a of n equal 1. You know 1 minus x squared is this formula, a of n equals m plus 1. What happens if you just keep multiplying by 1 over 1 minus x? What happens when you multiply by 1 over 1 minus x in a recurrence, in a generating function? This is a little easier than general multiplying because it's a very specific function you're multiplying by. Let's do this example specifically. What happens when you do this? Now's your chance, Doug.
Triangle numbers.
Yeah. What happens when you do this? What happens? What happens when we did this the first time? I'll call on you in a second, John. Just hold on. When we did this multiplication, we all know we got this thing here. Now we're doing it again. Yeah, John.
Should that be 1 minus x to the 4th on the bottom left there?
No, I wanted to do this one.
I thought I missed what we did before then.
Before we did 1 minus x to the 4th.
Yeah. Oh, I'm sorry.
Now I'm going back and doing 1 minus x cubed. I'm just doing something different. Before I was showing you what happens when you take two functions and you multiply them by each other in general. And here I'm showing you what happens when you just multiply by a very specific function, this one, 1 over 1 minus x. Because this does something very, very natural that comes up in the streams assignment that you did in Scheme. What does this do to this as far as coefficients go? Okay, right. It does what you called before, right. It does what you called before partial sums, right. If you stop at 1, you get 1. If you go 2 terms down, add up the coefficients. 1 plus 1, that gives you 2. If you go 3 terms down, add up the coefficients. 1 plus 1 plus 1, it gives you 3. Why does it do that? It's because multiplying by this is basically taking all of these terms that are here and kind of pushing them over to the right. Each one at a time. So multiplying by this gives you partial sums. So if we multiply it by again, we get more partial sums. If you multiply this by this, and you want to know what you get, the first coefficient will be the first one here. The second coefficient will be the sum of the first two here, which is the third coefficient will be the sum of the first 3. The next one is the sum of the first 4, etc. These are the triangle numbers. Anytime you multiply by this polynomial, the coefficients become the partial sums of the previous set of coefficients. And you did exactly this when you did the assignment in streams. You did something exactly like this. But now you can see it in terms of algebra. If you did it again, you'll get what's sometimes called the pyramid numbers. You'll get stacks of triangles, like the way you stack cannonballs. Right? You have a triangle of 3, and you put a cannonball on top, a triangle of 1. That's the first triangle number plus the second triangle number. That's a small stack of cannonballs. What's the next stack of cannonballs? You have 10 on the bottom, right? No, 6. 6 on the bottom, 3 on top of that, 1 on top of that. That gives you 10 cannonballs. Then you can have 10 on the bottom, 6 on top of that, 3 on top of that, 1 on top of that. That gives you the next stack of cannonballs. You can only stack cannonballs in triangular pyramids. If you try to stack them in square pyramids, they just fall down. So, yeah, I don't think you can stack them in square pyramids. I think they'll go. Right. You didn't see the Egyptians using nice square blocks for their, nice round blocks for their pyramids, right?
No, I did not study that.
All right, so something else you should know. When you multiply, you get what happened before. When you multiply by a particular function, you get partial sums. 1 over 1 minus x gives you partial sums, multiplying by that. All right, this is probably the hardest part of generating functions you can do. To make it a little easier, I'm going to do just one little diagram, and then I'm going to skip to something a little different. Uh-oh. Oh, there we go. One more, 1, 6, 15. This is Pascal's triangle again. I showed you how to get generating functions for each row. Those were finite generating functions. 1 plus x squared, 1 plus x cubed, 1 plus x to the fourth. What if you want a generating function for the diagonals? What's the generating function for this? 1 over 1 minus x. What's the generating function for this? 1 over 1 minus x quantity squared. Look what happens in the diagonals of Pascal's triangle. The next diagonal is the partial sums of the diagonal immediately above it and to the left. 1 plus 2 gives you 3. 1 plus 2 plus 3 gives you 6. 1 plus 2 plus 3 plus 4 gives you 10. We never noticed that about Pascal's triangle before, but it's certainly true. The next diagonal is the partial sums of the diagonal immediately above it. That means we've now got generating functions for every single diagonal of Pascal's triangle. Not only every row, but every diagonal. Questions about that? All right. What if I start multiplying by just x? This is even easier than before. What if I multiply by x? What does the new generating function look like? This particular one. Here's 1 over 1 minus x cubed. What happens? Everything gets bumped up one slot. So instead of 1 plus, we get x plus, these are x plus 3x plus, so it doesn't change all that much, right? It simply changes that whatever used to be, if we call this, say, d of n, whatever used to be d of n is now d of n minus 1. It just shifts everything over. It basically just moves the base case up 1. It doesn't do much at all multiplying by x. But it's a trick we're going to use later, so keep it in mind. If I take, say, this one, and I add it to this one, and I'm wondering, hey, what's that new generating function generate? Just look at the coefficients here, which are 1. The coefficients here, which are n plus 1. Add them together, you get n plus 2. And that's the new formula for the coefficients of your new function. So adding is easy. You just add up the formulas for the coefficients. Multiplying is tricky. You have to do that convolution of running through all the possible partial things and adding them, multiplying, adding all the multiplied pairs together. That's much harder, but adding is easy.
So if we were to multiply 1 over x times x, would be the generating function of x over 1 minus x. It's just subtracting 1 from previous?
Yes. Let me write that out.
That just seems kind of funny.
Okay. Let's see. Doug's asking this. He says, if I multiply this by x, that's just the same as subtracting 1 from
1 minus x.
That's what you said, right? Is it true?
Well, I was just looking at the function that if 1 over 1 minus x is just 1 plus x
That's
plus
right.
x squared.
So Doug has now discovered a 8th grade algebraic identity through graduate level topic in generating functions. You're right. What you said is right. You said this has to be true because of an argument in generating functions. That if I shift a generating function by x, it's the one I started with, take away the first term. And, well, we all knew that from much simpler ideas. I mean, just do the algebra. That's true. So you're right. And it seems funny, but it's true. It may seem funny, but it's true. Yes, good. All right. Everything's all the same in math deep down. There is no new idea. We're going to do one example, and this example is in the book. I'm pretty certain. At least it's in an old edition of the book. So, oh, sorry, it's not mine. So don't take notes. Just think about it. Just watch and think, because you can find this in the book. The other two examples are probably exercises in the book, but they're not in the book. And I'll do those next time, and you can just take careful notes on those. Here's the three I want to do. The one I'm going to do today is just a cool counting problem that turns into a generating function. We're going to get the generating function, make it look like one of the ones we just analyzed, and then get the coefficients from that. That's our goal. That's what we're going to do the next 10 minutes or so. Then we're going to use the same technique to solve a closed form for Fibonacci numbers, which we've done in a million other ways, but we're going to do it using generating functions. And then finally, the end of the whole topic is we're going to use these generating functions to solve that parentheses problem and to solve that binary tree problem to get an explicit number for how many of those things there are. And that's going to be a long thing. It's going to be generating functions, coming up with constants, a funny, horrible function. Finding the constants is going to need Taylor series. That's going to need about 45 minutes. And that you need a fresh brain for. So I'll let you clear out for a day before we do that. But now let me just work on this basic example that everything's going to come together in more or less a not too long of a way. So here we go. How many base 10 numbers are there? With n digits and an even number of zeros. It's a counting problem. You can write a recurrence equation for this. You could solve the recurrence equation using linear, non-homogeneous techniques. You could solve the recurrence equation using substitution. You could do all sorts of things with this problem from previous parts of this class. You could try to analyze this just straight up with counting. We're going to turn this into a generating function problem, manipulate the generating function, derive the constants, get an answer. So this will be an example of using generating functions to solve counting and recurrence equations. In this case, it's both. It's a counting problem and a recurrence equation. Okay so far? Okay, get on with it, you think. All right, so here's my recurrence equation. I'm going to call this number a sub n. A sub n is a number of base 10 numbers with n digits and an even number of zeros. And first, let's come up with a recurrence equation for this. This is sometimes the hard part. This is the part where everybody says, well, I don't know how to come up with a recurrence equation. So let's do it. I'm trying to get a base 10 number with n digits. I'm trying to have this depend on base 10 numbers with smaller numbers of digits. n minus 1 digits. Let's try that. Okay. Well, let's say I know how many base 10 numbers with n minus 1 digits there are that have an even number of zeros. I can add on another digit as long as it's not a 0. How many base 10 numbers of n minus 1 digits with an even number of zeros are there? Well, we don't know, but we just call that an minus 1. Right? It's the number of answers to our problem with one less digit. And each one of those we can add on the number, the digit 1, 2, 3, 4, 5, 6, 7, 8, or 9. So we have to multiply this by 9. But that's not all of them, right? Because what if the first n minus 1 digits did not have an even number of zeros in them? What if it had an odd number of zeros in it? Then we would have to add on a 0. But now we have to figure out how many n minus 1 digit numbers are there that have an odd number of zeros in them. How do you do that? The total number of n minus 1 digits minus the ones that have an even number of zeros. It's that complement trick. So add on the total number, which is 10 to the n. That's the total number, 10 to the n minus 1. That's the total number of n minus 1 digits in base 10. Take away the number that have an even number of zeros. That gives us the number with an odd number of zeros. How many with an even number of zeros? an minus 1. That's a recurrence equation. We're going to try to solve that now. We turned our counting problem into a recurrence equation, and we'll try to solve it. Sorry?
You do something to that, like multiply it by 9 or 10 or something? That's the number of...
No, that's it.
That second bit.
Because if we have an odd number of zeros for the first n minus 1 digits, Chris, then we have to put a 0 here.
Oh, you have to put a 0,
There's no other choice to make it an even number. So you only multiply by 1. That's it the way it is. Okay so far? Yeah, we're going to simplify it. We'll do it right here. So an equals 8an minus 1 plus 10 to the n minus 1. Okay, that's what you get. And what's the base case here? What's a1? How many one-digit numbers are there? With an even number of zeros.
So 0 even? Zero.
Zero.
An even number of zeros if you just have one digit. You always have. If you have
we're gonna say it's 9. Let's define it to be 9. There's 9 numbers that.
Zero is an even number.
if you have 0 zeros.
Right.
Yeah.
Right.
So if there are no zeros at all, that means there's an even number of zeros.
Right.
So
Right.
that's fine. Okay.
Yes.
Okay. The only single digit that doesn't have an even number of zeros is 0 itself, which is an odd number of zeros. Okay. All right. Take it or leave it. That's how we're defining it. We're going to try to come up with a generating function for this sequence. For the sequence, A0, A1. By the way, what's A0? Got no digits. We have to decide what this means. We have no digits at all. How many no-digit numbers are there with an even number of zeros in them? None. So we just say that there is no A0? No A0. Okay. So we'll start with A1. Fine. Here's a big generating function. You should know that when you do define A0, people define it to be 1. Okay, so if you wanted to define how many are there with no digits at all that have an even number of zeros, there is one no-digit number with an even number of zeros. The no-digit number. I mean, there's one of them. So here's what the generating function looks like. 1 no-digit numbers. 9 one-digit number. Anybody know how many two-digit numbers there are without zeros? Use this recurrence equation. Figure it out. I got 182. 82? Other people say 82? Should we do one more? Just to torture
Are
our...
you allowing 0 in the first place? In the first space?
0 in the...
So 0, 0.
Yeah,
one.
sure. Sure. $746?
Yeah.
You got to do 8 times 82, right? 8 times 82 is 656 plus 100, 7. All right, these numbers get pretty big fast. Let's not do any more. Instead, let's try to come up with an actual function that g of x is equal to. Turn that into something that looks like 1 over 1 minus something that we can deal with, and then get an actual closed form for our an. That's our goal. Ugh. Now, to manipulate something like this, we're going to need to use the summation notation, because it's very hard to manipulate this stuff and see what's going on without it. So this is going to be maybe about 5-6 lines of algebra, and then we'll get our answer. So watch what we get. It's the summation n 0 to infinity of a n x to the n. That's the fancy way of writing it. It just means the coefficients are the an's and the polynomials are the x to the n's. Those are the first few terms of this. Okay? A0 is 1. Let's do a little algebra. g of x minus 1. Why am I doing this algebra? I should motivate this a little bit instead of making it seem so magical. But the idea is that when you have recurrence equations that are based on one less, we're going to take this function and multiply it by x because it shifts it over. And then things start to cancel out and be nice. Just kind of like the geometric series subtraction trick. So in order to do that, the first thing we do is take the constant out. And then you're going to see that we can factor out an x. So we take the constant out. Now what's left? Let's write this out. N doesn't go from 0 to infinity anymore. It goes from 1 to infinity. And what's inside? Let's actually write out this recurrence equation. In place of an, we're going to write this. There's the x to the n. And in place of an, we're going to write what it equals. 8an minus 1 plus 10n to the minus 1. OK? I didn't do much yet. But if I had to manipulate this with dot, dot, dots, it would get ugly. So I'm manipulating it this way. Now I'm going to try to factor out an x from each of these terms, because then I get back to a situation where I start with a constant. So g of x minus 1 equals, let's split this up into two pieces. Let me do it step by step. I know I'm going to lose everybody if I don't just do it nice and easy. Here's the first piece, and here's the second piece. OK, I just split up the two sums. I separated them out. OK? Next step. Now pull out an x, and in this case an 8, from these terms. What do I get in the first term if I pull out an 8x? N equals 1 to infinity of an minus 1 xn minus 1, right? Because I factored out an x. So all the xn's turn to xn minus 1s. And here, what do I get if I factor out an x? 10 to the n minus 1, x to the n minus 1. Almost finished, believe it or not. I'm going to rewrite this thing a little bit here. If my n starts from 1 and goes to infinity, and this is an minus 1 x to the n minus 1, then what are the actual values of the indices here? When n is 1, this is a 0. And therefore, I'm really starting here at 0 and going upwards. So I'm just going to rewrite this a little bit. Instead of writing n equal 1, n minus 1 here, I'll write n equals 0 to infinity, and I'll change these n minus 1s to n's. Because this will look a lot like what we've had before.
Should you change that n to like a different letter, maybe?
Because you like eyes?
Like, yeah, so
I've been using n's the whole time, though. Oh,
you're
because
saying that this new n is equal to n minus 1.
oh, because I used n here.
Oh, but you went back to 0. All right. I'm back. I'm back.
No, I'm not. Yeah, I'm not doing anything
All right.
fake.
Shouldn't be n minus 1 anymore.
N here, right? Right, I'm just changing all the n minus 1s to n because now n is starting back at 0 instead of 1. In other words, these are really generating functions again that have constant terms, and I want you to see them that way. Okie dokie, almost finished. What is this? That's g of x. That's the original recurrence equation that I started with. That was the whole idea of doing this algebraic manipulation, is to shift over, plop around, and get what I started with. This is the sum of all the a(n) starting from 0 going to infinity in front of the x to the n polynomial terms, and it's a0, a1, a2, a3. That's just what I started with. So I get ax times gx. That trick is very much like doing geometric series. You take away the constant term, you factor out the x, you look really desperately for what you started with, and you hope you find it. Oh, but now I got this thing. Oh, geez. X times, what's this?
Series with.
This is the generating function that has 10 to the n in front of the x to the nth term. What's an easy way to write that function? 1 over 1 minus 10x. So that infinite sum now turns into something finite. That's why I spent all that time at the beginning reminding you that we're looking for stuff like this. We're looking for stuff where the something to the n goes with x to the n, because you can convert it back reverse into a geometric series which gets rid of the infinity. If you're thinking, God knows I can barely follow this step by step, how would I ever do it on my own? That's a completely natural feeling. This is a deep topic. It really is. And you're going to get 2 days on it, and you'll see some cool things with it, and you'll be expected to do a couple problem sets with it. You're not going to be expected to be expert with this stuff, but you'll appreciate it at least. It's a really cool topic. Here's what we get now. Gx minus 1 equal 8x gx plus x times something finite. We're almost finished. We're going to get a value for gx in just a second. All right. I don't enjoy doing really complicated things and making you feel like you're in a jungle. I don't like it. There's no other way to do this the first time. It's just hard. Let's solve for g of x here. Let's get all the g of x's on one side. So I'm going to pull this over here. What do I get? This is what I get. 1 minus 8x g of x equals x over 1 minus 10x plus 1. Okay, I put all the g's on one side, and I factored out the 1 minus 8x. And now I get g of x. Look, we're almost done. Look at this. This is so cool. Let's, add this together for me, somebody. 1 minus 9x over 1 minus 10x. Is that right? Okay, so now I get g of x equals 1 minus 9x over 1 minus 8x times 1 minus 10x. You wish to God we were done right now. We were going to be. What are the coefficients of that? We didn't have the slightest clue. But now I can refer you back with a one-step deal, because I know you all know how to convert this into partial fractions, right? Remember that? You don't remember. It doesn't matter. What was that? I missed a good one, huh? Add those two on the right together. You'll see you get the thing on the left. I'm skipping the steps of how you'd find it. You'd find it by partial fractions. You'd set this up into two fractions. You'd find out what the top pieces are. And you'd find out that both top pieces are a half. You can multiply it out and check. It better work. Yes, you get 5x. It better work. All right. Now, why do we want to do that? Because these things, you know what coefficients they build, right? Those are those basic building blocks that I spent time explaining before at the beginning of the day. 1 minus 8x, 1 over 1 minus 8x, that generates powers of 8. 1 over 1 minus 10x generates powers of 10. So here's what I'm going to do. I'm going to factor out a half, get 1 over 1 minus 8x, 1 over 1 minus 10x, and finish up like this. Therefore, my coefficients, an, are 1/2, whatever this generates, plus whatever this generates. This generates 8 to the n, and this generates 10 to the n.